Thank you for joining. Uh, my name is Ramakant Sharma. I am co-presenting with Rishabh Soni. We are engineers at AccuKnox and we are maintainers of KubeArmor, a CNCF sandbox project. We have reached the final stage of this amazing event. And so last thing last, let's discuss the last layer of defense called runtime security. Let me quickly put the agenda of today's discussion. We will start our discussion with runtime security. Then we will move to the main topic of today, which is Linux security modules. Why someone will use LSMs to implement a runtime security engine. Then we will discuss these three major LSMs, SELinux, Apparmor, and BPF-LSM. Then, and as KubeArmor uses LSMs for the enforcement, we will discuss KubeArmor. Then from the KubeArmor's perspective, we will explore use cases, what KubeArmor provides using each LSM, and then we will discuss the operation complexity that we came across while implementing KubeArmor. And then in the end, we will discuss performance. So let's start by discussing runtime security. Why it is important? Because runtime is where an attacker win or lose. So most of the attacks, they achieve their end goal in the runtime. If we look at the major attacks like remote command injection, ransomware attacks, and crypto mining attacks, they target the execution environment and execute their malicious intent in the real time. So then naturally runtime becomes the most critical phase to protect. So let's see how runtime fits into the broader picture of cloud native security. Protecting cloud native applications involves securing them across these four critical phases. And security measures implemented at the phases prior to the runtime, they are static in nature, like dependency management, vulnerability management, supply chain security, or admission policies. They aim to prevent non-risk or non-vulnerability from reaching the production in the first place. But here's the issue. What if something gets through? An overlooked weakness or an unknown zero-day vulnerability that can easily bypass these static security checks, right? So, and when that happens, it can result in a runtime disaster. That's why the runtime security becomes the last line of defense. But runtime security is fundamentally different. It requires dynamic controls. It requires continuous monitoring of the application and ability to enforce the security in runtime. So the natural question that follows is, how can we actually enforce runtime security effectively? So to answer that question, we need to understand how Linux enforces access control. These are two common types of access control in Linux, DAC and MAC as they're called. Discretionary access control is a traditional Unix style user group permissions, where user can define permissions like who can access their resources and with what permissions, right? And but the caveat here is there is a super user root that can bypass these access checks. So to go beyond DRC, what Linux introduces MAC, mandatory access control, through the LSM frameworks. So unlike DAC, MAC policies are strict access checks, the policy defines security, and even the root user cannot override them. So here's how the access check sequence looks like. So first the access request enters into the kernel, and then the kernel checks for the DAC permissions. If that is fine, then the control goes to the LSM, and the control goes to the LSM, and based on the operation, a particular LSM hook will be triggered. And all the major LSM and modules like Apparmor, BPF-LSM, and SELinux, they comes into the picture at this point. That request will go to those LSMs. They will evaluate that request based on the security policies that they enforced, and they provide a result like whether this access should be allowed or denied. So based on that decision, the MAC decision is made. Let's see how the access check looks for a binary execution. The binary execution request enters into the kernel. Then the kernel checks for the DAC permissions. If this is allowed by the DAC permissions, then the control reads to the LSM hooks. Specifically, in this case, BPRM check security is the LSM that will be triggered. And then all the active LSMs, like Apparmor, SELinux, they will evaluate this access against their security policy. And then the final decision will be made across all these active LSMs. If any one of them denies the execution, the overall result will be denied. The important point here is till this point, process has not started the execution. Only if it is allowed by the LSM, then only the process will start the execution. So now we have seen how LSM enforces access at runtime. But now let's talk about why LSMs are essentially well suited for enforcing runtime security, particularly compared to other methods. What really sets LSM apart as a runtime security mechanism is their ability to perform inline mitigation. Many other enforcement approaches, especially those operating in user space, they suffer from an issue called talk to issue or time of check to time of use delays. Here is what it looks like. You detect a suspicious action in user space, then decided to kill the pod or the process. But by the time that decision is made and executed, it already may be too late. The attack already may have done some harm. So, even if you use something like BPF send signal to send a kill signal to kill the process, there is still a small window of delay. And the attacker can use this delay to access the resource. But in contrast, LSM operates inline inside the kernel's decision path. If a policy denies an action, the operation is blocked immediately before it even happened. So there is no window, there is no raise, no talk to vulnerability in case of LSMs. And that's what makes LSMs ideal for runtime security enforcement. Let's discuss these three major and widely used LSMs. Let's start with SELinux. SELinux uses a label-based access control model, which means every process and resources like files, sockets, network sockets, and network ports will be assigned a security label. And the access will be allowed using the SELinux policy rule defined these labels.
Definition is a statement of the meaning of a term. Definitions can be classified into two large categories.
Sorry for that. And the access is allowed using SELinux policy rule defined with these labels. Access is allowed only if a matching policy rule exists. So these labels are stored as an extended attribute on the file system. So it uniquely identifies the resources. So unlike path-based modules like Apparmor, SELinux is not vulnerable to bypass using symlinks, hard links, or bind mounts. Why it's not? Okay, so in this example, the Apache process is running with this particular SELinux type, right? And the particular directory that Apache servers required access to is assigned a specific label. And the access between these two resources is defined by a particular SELinux rule. So even if the Apache process got compromised in the real time, user cannot escape outside this confinement. So the other resources, other host resources like etcd password file, that is a sensitive asset. User will not be able to access that. Let's look at how SELinux extends its labeling and isolation model to protect containers. In this example, we have these three containers. Each container process is confined using a SELinux MCS label, multi-category security label. So the process inside the containers are labeled with these context. So each container can only access the file system that has a matching MCS label. So, but there's one exception that we see, which is the second container, which is has a specific label SPCT, right? So this is how, in general, SELinux handles the privileged containers. So this special case is, so this typically represent a privileged container, the second one. For example, one that needs access to host files or kernel interfaces, those containers will also be handled like this only. So in this case, the container bypasses the strict type enforcement that SELinux normally provides, which weakens the isolation. While SELinux can handle such cases by assigning a unique type and writing custom policy rules to allow specific access, but the problem is this will quickly become complex to manage at a scale. SELinux is designed to protect the host from the container, and it does that really well. But what if the container application itself is under attack? Once an attacker gains access inside the container, SELinux policy don't restrict the process accesses within the container. So attacker can move literally inside the container. He can explore the file system, access secrets. So here, what more container-aware solutions we needed. So now let's look at Apparmor next. Unlike SELinux, which uses a global label-based model, Apparmor confines each application using a dedicated profile. This makes it easier to manage. Policies don't interfere with one another, and each service has its own sandbox defined independently. But Apparmor's model is path-based, not a label-based. So it evaluates permission based on the file paths, which means you need to explicitly handle edge cases like symlinks, hard links, and bind mounts. If these aren't accounted for, a process may access a sensitive file by simply reaching it through an alternative path. Here's a simple example of a Apparmor policy that targets the Nginx service. It denies the access to sensitive asset like etcd password and etcd shadow file. And it also blocks powerful capabilities like sysadmin. This example shows how Apparmor can confine the behavior of a containerized application inside Kubernetes. In Kubernetes and also in general, the container runtimes like containerd, CRI-O, or Docker, they are responsible for attaching the Apparmor policies profile. The containers process when it starts. So in this case, we have a container running Nginx. We have attached an Apparmor profile. The policy explicitly denies execution of user bin apt and user bin apt get. So if the binary exists inside the container, it won't be allowed to run. So Apparmor intercepts this at the time of execution and block it. BPF-LSM allows runtime instrumentation of the LSM hooks in a programmable manner, unlike SELinux or Apparmor, which rely on a static policy format and predefined rules. With BPF-LSM, we are not limited with predefined controls. BPF-LSM allows attaching to any available LSM hook. So for example, here in this code segment, we use BPRM check security hook, and which is triggered during the process binary execution, allowing us to inspect the binary, and we can place our own custom logic here and then choose to deny or allow the execution. Important point here is that BPF-LSM is inode-based access control. This means decisions are made based on the actual kernel objects, not string paths. So it avoids issues like symlinks or bind mount escapes that affect path-based controls like Apparmor. To apply BPF-LSM for container workloads, we need to identify which process belongs to which container in kernel space. And containers are user space abstraction. But the kernel gives us primitives like C groups and namespaces to map a process back to its container. So once this mapping is in place, we can enforce fine-grained controller-specific policies directly from the kernel, all within BPF-LSM. So now we have understanding of how LSM works and how we can enforce security policies using those. Let's explore KubeArmor.
Yep. We mentioned KubeArmor earlier. KubeArmor is a runtime security project. It's a CNCF sandbox project which helps you restrict file, process, capabilities, syscalls, and network operations for your application. KubeArmor, we talked about LSMs. LSM is what helps KubeArmor to actually restrict all these operations. But for runtime collection of alerts and events, KubeArmor uses eBPF hooks as well. KubeArmor provides a Kubernetes CRD-based policy structure, which we'll talk about more in the coming slides. We have a helper CLI called KArmor, which will help you set up KubeArmor in minutes, and it will help you with log collection as well. And with the telemetry alerts that you get using KubeArmor, you can actually ship them to OpenTelemetry, Elasticsearch, etc. So as I said, we are going to explore all these capabilities of KubeArmor, mainly process file network control capabilities, syscalls, and my favorite, advanced security controls, which we call presets. So this is what a typical KubeArmor policy structure looks like. On the left, you see process. In the middle, you have file. Explaining one of these would suffice for both because they basically have the same structure. You have match path, where you would basically match a path, absolute path for a file or a process. You have owner only. So Ramakant discussed DAC earlier. Imagine that you have a process which have a user, the owner of the user, which you want the user to actually access the file. You can actually specify in the owner only field, and the user would be able to access the file, but anybody else would be denied. From source. So let's say your application itself is trying to access a file, but it's a sensitive one, right? Ideally, you want the application to access the file, but anyone else should be denied. From source actually helps you specify a path which allows the application to access that file or a process. We have match directories as well. Let's say you have a directory where you have a number of sensitive processes or binaries, or you have files. You can actually use match directories to deny them. You can be recursive as well. Owner only and from source are supported as well. Match patterns. So you have a pattern-based naming convention for your applications or files. You can use that as well. We use the asterisk pattern here. And yeah, we have network on right side. We support all protocols, whether it's TCP, UDP, ICMP. We also support filtering raw sockets. And capabilities, you can use the match capabilities option to actually specify a capability that you would want to deny your application, or maybe you want to allow them that capability and deny rest. Syscalls is, again, self-explanatory. You have the same fields. You can specify syscalls, and you can filter them. On the bottom left, you can see presets. We have different kinds of presets that I'm going to discuss in the future slides. But what the policy structure actually specifies is basically allow, block, or audit-based actions. Enforce predefined security controls using audit or deny policy for a specific execution event for hardening policy purposes, right? Zero trust policies. This is what you would typically use in a production environment, and allow only behavior is expected out of the application. Audit and block are outliers, right? It's a least permissive policy style, whitelist access to sensitive assets. So this is what a typical block policy would look like. On the left-hand side, you can see there is a kind, which is KubeArmor policy, and it is denying an application of its package managers, which is apt and apt-get. On the left, you can see that a user actually exit into the pod using spawned a bash shell. They tried to use apt, but they got a permission denied. And on the right, you can see that you have a rich telemetry event. I would call this rich because if you notice carefully, then you have the PID of the actual apt process that got denied. You have the PPID of the apt process. You also have the host PID, and you also have the host PPID. Why this is useful, in my opinion, when you have number of containers running on your clusters, you have number of namespaces, nodes, etc., it becomes complex to actually point out an event, but this telemetry event, in my opinion, actually helps you point that out. Let's talk about zero trust policy. This is what I talked about earlier, which is an allow-based policy. In this, you can see that we have a lot of paths, controls mentioned, which are actually allowing, blocking as well. And on the bottom right-hand side, you can see that there is a match labels option. This is what actually helps KubeArmor to select what pods / deployments / stateful sets you want to target with this policy. So this is a very comprehensive policy, and this would, what I would call is a whitelist policy, and helps you scope out directories, permissions specifically for your application. Let's talk about the favorite topic of today, which is presets. Just a quick introduction of presets. Presets are special security controls that are built into KubeArmor policy. And for example, this one here is protect env, and you can see that on the right-hand bottom side, we have protect env block. And what this basically does is that you can imagine that, or it's actually a fact, every process in Linux have a proc directory to itself, right? And ideally, let's say if a process is trying to access another process's environment variables, I would not consider that very safe, and that should be ideally denied, right? And this is what is exactly being done right here. You can see that a process is trying to cat environment variables of a process, and it's being denied, right? So fileless execution. So whenever, if you have run a script using curl and pipe that to bash, that does not actually, and if it's a fileless exec event, then that basically introduces all of the commands into the memory directly, and nothing gets saved into the file system, which is the secondary storage. This is a very common attack surface, and using KubeArmor presets option, you have the fileless exec option, which is into block mode right now. And we have a demo Python script, which is basically trying to do a fileless exec attack, which gets a permission denied. Protect proc file system. This is similar to environment protect and env. And so, but this actually helps you restrict complete access over other proc directories apart from the process's proc directory itself. So let's say that somebody is trying to understand what all threads. We have a thread directory in the proc directory itself of a process, right? And somebody is trying to gather the information using another process. Well, if you have protect proc preset running, then it would be denied. Let's talk about limitations.
There are certain limitations that we came across, specifically with the Apparmor for policy enforcement. One is like Apparmor does not enforce policies on the immediate child. So on the left, you can see that we try to, like on the right, there is a Apparmor policy that denies the access of apt and apt-get, right? And on the left, you can see that we tried to access these processes. First, we tried directly by by spawning a bash shell, right? And then we try to access this apt, and we see that the permission got denied, right? And in the second attempt, what we just did is we directly access the apt binary without even spawning a shell, bash shell. So in that case, this becomes the direct process of the container. This is the initiator process. So Apparmor is not able to enforce the policy on this in this case, right? Another limitation is like when we deploy our containers with a special flag that is allow privilege escalation. So when this particular flag is set to false, and we try to enforce a specific policy that also has a sub profile. In this case, we have a KubeArmor policy that defines that bin ls. Bin ls is the binary, and this should not be accessed if the parent process is bin dash. So when we tried to enforce this, when we tried to execute this, the ls got permission denied. But we also see that also when we try to execute the dash itself, the process is in blocked state. And this is not happening because we have a policy. This is happening because Apparmor is not able to transition to its sub-profile that we defined for the dash itself. We can see the error that we got is operation not permitted. That simply tells that the dash binary or the dash process is not able to acquire the capabilities that are outside from its current capability set. There are certain complexities associated with deployment, policy management, and telemetry and integration that we came across while implementing KubeArmor. Let's discuss these in more details. As KubeArmor need to be present on each node, as it leverages the active LSM present on the node, it has to be deployed as a daemon set. But in the real world, KubeArmor clusters aren't uniform. Kubernetes clusters aren't uniform. You might have Ubuntu nodes to run GPU-heavy AI workloads because of their NVIDIA stack compatibility. You might have some nodes running on Bottle Rocket from AWS, and each of these nodes will be different in terms of LSM configuration. So accordingly, they will require different daemon set configurations. So it's not a one daemon set configuration fit for all these different requirements, right? To solve this problem, we use a Kubernetes operator pattern. So here we deploy KubeArmor operator, and that inspect each node's configuration in terms of active LSM and dynamically generate a daemon set accordingly for that particular node. This is the complexity associated with the policy management. Policies are being, in case of BPF-LSM, policies are being managed in a decoupled manner using the UPF maps. So policy management does not require application restart in this case. But whereas in case of Apparmor, the policy management involves resource updation operation. For most of the resource, Kubernetes follows rollout strategy for the updation. But if we do it for many resources concurrently, then it could lead to CPU spikes, and if readiness probe is not configured accurately, it will lead to slight application downtime. Here with KubeArmor, we handle these by restarting the deployments and certain other resources where pod is being managed by a parent controller. But there is no rollout strategy for static pods, right? So KubeArmor handles this case only for the new pods using the mutation webhook and modified that pods at a pod binding event. We are also limited by the stackability. For multi-layered security, more than one LSMs can be stacked together. But Apparmor and SELinux, they are not stackable. They will interfere with each other. So on a system, we cannot enable these two different LSMs at the same time. But on the other hand, BPF-LSM is a stackable LSM. And in terms of using LSMs, we are limited by their availability based on the kernel version. So we can, if you want to use a BPF-LSM, there's nothing we can do but updating our systems, right? Because that only available on the newer kernel versions. But what if an LSM is present but not enabled on that node, right? So that involves updating nodes. And to make sure that we done that safely, there are tools like Curate that helps for safe and automatic node reboots. KubeArmor provides telemetry alerts we just saw. So in the case of policy violation, in case of BPF-LSM, The detail of the event is present at the time of denial. So the enforcer sends that event to user space using ring buffer. And KubeArmor just generate that alert. But in case of Apparmor, we don't have a way to get the alert directly in kernel space. So we did explore these user space solutions, but the problem is they require pooling method to get the alert events. So what KubeArmor does is it matches the events observed by the system monitor using a deterministic policy matcher and generates the alerts accordingly. Here we have come to the performance. This is the popular opinion that, and in the increasing order of the performance overhead, EBPF, Apparmor, and SELinux tend to introduce the largest overhead. But the point of discussion is to suggest that real-world performance might different on specific use cases, configuration, or test condition. The result published in this research state that Apparmor may introduce higher overhead than SELinux for some of the file operations. Similarly, this result suggests that enforcer may behave differently based on the application load. Within a 10-second delay between the request, the peak shift to 0.8 to 1 range, but notice something interesting here. The spread of high latency shrinks. So even if the peak looks higher, this suggests that the average application load performance will be stabilized. Thank you. That's it. Any questions? Yeah.
Excuse me. Excuse me.
Hello.
Yeah.
So it's a great presentation. So for KubeArmor, what I understood, it has functionality for the Apparmor or that similar LSM. At the same time, we can do monitor also. So there is a classic tool also we have like the Falco for the monitoring. So from the only aspect of the monitoring part, so if we need to compare between Falco and KubeArmor, so is there any advantage on top of Falco? I mean, using KubeArmor?
If you are considering only monitoring part, then both are the same product, right?
Okay.
We also leverage eBPF to observe the application behavior at runtime. The differentiator of KubeArmor is how it enforces the security policies, right?
Got it.
And
one more question.
Yeah.
So another thing for the enforcing policy, so it works on the runtime basis, like through admission controller. So is there any way I can avoid this admission controller if I can apply those manifest at the CI level only? So is there any way to do that? So just I want to avoid these runtime level checks if you can do that similar thing at the CI level.
no, you can't do that. So what you can do is you can have a set of policies. We also do that. We created hardening policies. You can specify certain block rules, right? In production, those should not be allowed. For example, package managers, right? apt and apt-get and rest of the package managers. You can define a runtime policy that you don't want in the production, any of the containers should not execute those package managers at runtime, right? So you can apply those policies.
Got it. Okay, thank you.